And here's our warm-up. Question 1 is a calculator question. When you get sine theta by itself and get negative 2/3, that is not on your pie plate. So you're going to have to find reference angles, use your cast rule. I'll put up the answers in a bit. Find a reference angle. Remember, when finding a reference angle, you do sine inverse of positive 2/3. We always use positive with reference angles. Once you have that reference angle, now, according to your cast rule, you have to look in quadrants 3 and quadrants 4. I'm going to just quickly add one more decimal place because I would lose a half a mark for rounding here.
I'm going to go into these.
So we should have a 3.871. There we go, and it should be 5.553, correct to 3 decimal places. Second one, again, get tan by itself and find your reference angle. How many people have done the second one already? On this second one, did you get your reference angle to be 0.359? Again, when we find a reference angle, you do tan inverse of the positive. And then once you have that reference angle, tan is negative in quadrants 2 and 4. And I should have that extra decimal place. Does someone have it? What's after the 8? A 3? And what's after the 2? A 5. Perfect. So again, this is all stuff we have from chapter 6. This is the expectation. It's using stuff from grade 11. The only thing different from grade 11 on these questions is that we're in radians on our calculator and using pi and 2 pi instead of 180 degrees and 360 degrees. So we haven't added a lot. Now we're going to go to a couple that are non-calculator. Now we're not allowed to use our calculator, and we're supposed to solve. Non-calculator usually means there's going to be something from your pie plate. But is 4 on your pie plate? How do we do this one? Because we do get cos theta equals 4. And 4 is not on your pie plate. How do we do this one? It's actually quite easy. It's not possible. Because if cos theta is 4, which you think of as 4 over 1, and you try to draw a right-angled triangle with the adjacent side 4 and the hypotenuse 1, this is a problem. Because you know the hypotenuse has to be the longest side. So anytime sine or cosine, not tangent. Tangent's okay to have the opposite side bigger than the adjacent side. But anytime sine theta or cos theta is bigger than 1. Technically, also any number bigger than 1 with a negative in front would also be true. Positive or negative, you can write not possible. And now we're going to introduce something new. This is chapter 7. This is what is new. Chapter 6, they always gave you a domain. 0 to 2 pi. Sometimes in your homework, you notice they went negative 2 pi to 2 pi, like extra annoying because you had to find more answers. That was chapter 6. Chapter 7 is saying, let's just do everything. Right? From 0 to 2 pi, normally you got 2 answers. And then negative 2 pi to 2 pi, you got 4 answers. If you kept going on forever, you're going to have an infinite amount of answers. And although this is new, the only new thing it does is it combines two things in chapter 6 that you already know. So technically, it's new but not new at the same time. So first of all, if you get a question with solve for everything, which is our new idea, we're going to start solving just like normal. Start by just solving between 0 and 2 pi. We're going to get our reference angle. Is that on our pi plate? Yeah. Yes, because it's non-calculator. Technically, you might recognize this as the same as negative root 3 over 3. So you know that it's your pi over 6 family, and since it's negative, those would be your answers in quadrant 2 and quadrant 4. So we're going to find out that even with the new one, we're going to just solve like normal, like we normally do, from 0 to 2 pi. Now, if we took out our unit circle and said, I have an answer here at 5 pi over 6, and I have another answer here at 11 pi over 6, and that's the first time around. The second time around, I'm going to hit another answer here and here, and then another one here and here and here and here and here and here, and keep going forever in the positive direction. And then I'm going, oh, I could also go in the negative direction. So if I go negative, I could end here and here and here and here. And if we hit all of those same places over and over again, what do we call an angle that ends in the same place as another angle? Coterminal. And what we're really trying to find in this solution is not just these two answers, but every answer that's coterminal with it. And that's something we also did in chapter 6. How did we write an angle and all of its coterminal friends? Do you remember? We would say, oh, I could take 5 pi over 6, and to get coterminal, I have to go all the way around, which would be adding 2 pi. And I could add 2 pi, right, there's a nice visual. I could add 2 pi as many times as I wanted. I think in chapter 6, we went 2 pi and then put the k at the end. And in chapter 7, they're like, this time we like the k in the middle. It really doesn't matter. But you tend to see it more often with 2k and pi right at the end, rather than 2 pi k. They're identical. All we're doing is adding multiples or subtracting multiples of pi. Technically with tan, also from chapter 6, what's the period of tan? Right, period of sine and cosine is 2 pi. What's the period of tan? Pi. And what you might always notice is that tan is the only one where the positive ones, oh here we go, the positive ones are directly opposite each other, the negative ones are directly opposite each other. That's because tan repeats itself over pi. So this answer that we have right here, taking both of our answers and adding 2k pi, full marks. Okay? If you left it like that, full marks. I'm going to show you that for tangent, you could write it even more elegantly by saying, if you start here at 5 pi over 6, and go halfway around, you'd get to 11 pi over 6. And then halfway around again, you'd get to the next coterminal one here. And half and half and half and half. So you could combine both of those two answers by just doing jumps of halfway around. And this looks, as an answer, looks more elegant. Okay? If it's a long answer question on a test, a quiz, or your exam, you're able to write it either way. I have seen, though, on the exam, sometimes a multiple choice question, where they've written it in the more elegant way, and if you haven't seen that before, you get confused. And here's the hypnotic diagram to show you those jumps. So with that introduction, I'll get you to turn to the top of page 574. Oh, first of all, we are going to slightly change the title to this section. We're going to take out the word graphically, and we're going to change the title to this section to the general solution. And then we're going to turn to page 574. And at the top of page 574, we're going to write out the steps for solving a general solution, sort of to summarize what we did in that last question. We're going to solve sine theta plus 1 equals 0. And so again, this isn't on your unit circle, so you'd have to go sine inverse of positive 1/7 on your calculator to get your reference angle.
How do you know if it was calculating around?
If it doesn't say, now that you're in higher level mathematics, they'll assume radians. Okay?
So,
But usually you look at the domain,
okay.
and that would tell you degrees or radians.
Okay, so
And if it's not stated, and you're in a higher level math, assume radians. If it's not stated and you're in a lower level math, assume degrees.
You mean not stated like the domain?
Like here it says, the domain is stated. It says theta is all real numbers. But it didn't say all real numbers in degrees or all real numbers in radians.
Okay.
Okay, so we'll assume radians.
Okay.
As like basically, if it says that, assume radians for this class.
Yeah.
Like a pi usually would be
In degrees. Okay, so now we solve like normal. Where's sine negative? Quadrants 3 and quadrants 4. I have 2 decimals. I'm going. I should add one more decimal. Sorry, I will do that. Sine. You know what? It's good that I only have 2 decimals, because then I really have to explain to you guys how important 3 decimals are every time. Pi plus my reference angle, 3.285. Interesting. If it's a 5, does that mean I rounded wrong to begin with? Should I have had a 9? No, because it was actually 3.2849. Oh. And the second one, 2 pi minus my reference angle, 6.1. Oh, this one should be, oh no, it's okay. 140.
Wait, how do you, like, what are you doing?
So here, what I'm not doing is I'm thinking about my casserole, and I'm thinking about here and here. And then in my head, I'm imagining quadrant 3, and quadrant 3 would be pi plus my reference angle. Right? Because this is, up here is pi, and here's my reference angle. So if I want quadrant 3, I have to do pi plus my reference angle. And in quadrant 4, so I have another one in quadrant 4, here's my reference angle. I would think going all the way around is 2 pi, and then I would have to subtract my reference angle. So this actual angle here is 2 pi minus my reference. Okay? But now that we're done chapter 6, once you get to chapter 7, the idea is like you know this already, you can just do it in your head. So we get our 2 answers, then the general solution says, take your 2 answers and add 2k pi. So this last step is the only thing that's new. But all you're doing is writing all the coterminal angles for the one answer and all the coterminal angles for the second answer for your final answer.
For the like the last part, are we supposed to keep it to 3 decimals or just?
Yes,
Okay.
Everything.
Everything. Thank you for
Everything
noticing.
has to be 3.
there we go, 3 decimal places, 3 decimal places. Perfect.
Mr. JR.
Yes.
Do I have to both state what theta is equal and do the 2k pi, or could I just put them into one step?
Like, you figured these out and wrote them here and then went to the plus 2k pi right away?
Yeah.
That's fine. Sometimes though, you're gonna find yourself, especially when it's on your pi plate, you're just gonna be in a rhythm to solve first between 0 and 2 pi. And then, sometimes even at that moment, you're sort of like, what was the domain of this question? Oh, it's a general solution. Then you come back and have to write them. So I'll always solve first between 0 and 2 pi for that reason. All right, here's our second one. We're gonna have 3 examples for example 1. There's still example 1, you can call it B if you like. First one could be A, this can be B. We're gonna have 3 examples replacing example 1. If you're running out of room,
Just take over.
there is a whole blank page that you can use, well, on page 570 going back a little bit, or there's a blank page at 583. Yeah.
Oh, okay.
This course used to be graphing calc, because all of this is on the graphing calc.
There's a bunch that uses graphing calculator, and we use a graphing calculator because we're going to get ready for the AP course as well. The whole idea, technically everybody should be taking this course while they're in grade 11 so that they're ready for AP calculus next year.
Because usually AP isn't really AP, it's just calculus.
It's just calculus.
Which is the high school course.
Yes, but in order to fit it into your schedule, you need to be done grade 12 pre-calculus by the end of grade 11. And generally, the whole name of pre-calculus, the reason you should be taking pre-calculus courses is because you're planning on taking calculus or doing something in university that requires some higher math.
Is that just calc 1 or calc 1, 2?
It's mainly calc 1.
Me? Nothing? I'm on a red river, what are you talking about? I don't need calculus. Well, they require like essentials or something.
For this one, I want you to try it on your own. I will just put the final answer up there when you're done. See if you get it.